Assalamu alaikum and good afternoon. Today we will be presenting two mini projects for our CSE 106 course Discrete Mathematics. My name is Mohammad Mustafa Hossain and my ID is 2025160267 and my other two members are Mahmudur Rahman, whose ID is 2025160318, and Nazmul Hossain Siam, whose ID is 2025160181. Our first project is an empirical analysis of time complexity of linear search algorithm. Our objectives are: first, to implement the linear search algorithm. Second is to measure its average execution time across different input sizes empirically. Third is to compare these real world measurements with the theoretical complexity we learned in the class. And finally, to visualize this relationship using a plot with a straight line. Methodology. Our methodology was straightforward. We implemented linear search in Python. We then generated random arrays of increasing sizes from 10,000 to 50,000 elements. For each array, we performed 1,000 searches for random targets within that array. After that, we recorded the total time and calculated the average time per search in milliseconds. Lastly, we plotted these average times against the input sizes. So Python code snippet. So this is our code. First, we used a main loop to iterate over each array size we want to test. For each size n, it generates a random list of n integers, and then it creates a list of 1,000 random targets values to search for. Then it starts a high precision timer. After that, it performs all the 1,000 searches by calling the linear search here, a function for each target. It stops the timer and calculates the average time per second. So after calculating the data for all sizes, it uses linear regression to fit a trend line to the data points. This gives us the slope and intercept for the red line on our graph. So now we will be showing the graph. So this is our graph. The plot makes this linear relationship undeniable. The blue dots represents our empirical data, the actual measured times. The red dashed line is a linear trend line generated using linear regression. The equation of this line is y equals to 5.00 e minus 0.5 into n plus negative of 0.03. confirms a direct linear proportionality between time y and input size x, which is the array. The very small y intercept is negligible, and further emphasizing the linear relationship. So discussion. Our discussion is simple. The data speaks for itself. The average execution time increases linearly with n. The trend line we calculated strongly confirms big O of n behavior. This empirical result is a perfect match for the theoretical average case time complexity of linear search, which is big O of n. So thank you. Now we will move on to our second project, which applies graph theory to model a social network. Our project is a friendship graph simulation. Problem statement. The problem was to simulate a social network. We model users as nodes in an undirected graph with friendships between them as edges. We generated graphs of different sizes, 500,000 up to 2,500 users. Friendships or edges were generated randomly within a certain probability to create a realistic network. Tasks to perform. For each generated graph, we had several tasks. Compute the degree of each vertex, essentially counting how many friends each user has. Use this to verify the handshaking theorem, a fundamental concept from graph theory. Then we had to find of the number of connected components in this graph, which represent isolated graphs of friends who aren't connected to the larger network. Then finally, we had to plot how many number of this component changes as the network grows using matplotlib. So we will move on to our code. here, as you can see, to conduct the um, B1 friendship, for the friendship graph we use a powerful library called Network X, which is built for creating and uh, analyzing networks. The function generate friendship uh, graph creates a graph with n nodes. The key part is the nested loop that considers every possible pair of users I or j. Mm, it then uses a random number checked with a fixed probability to decide if an edge should be created between them. This is a common model known as Eddos-Renyi random graph. The main loop then runs this function for each of our network sizes. For each generated graph, it calculates the number of connected components using a built-in network X function. Uh, then it verifies the handshaking theorem. It calculates the sum of all degrees of each node. The theorem states that this sum must be equal to 2 into sum modulus of edges, twice the number of edges. We use an assert statement to automatically check this. If this were false, our program would crash, telling us there was an error in our logic. It never crashed, confirming the theorem held for every graph we made. It records the number of components for plotting. So finally, the connected components against the number of users showing the trend we discussed is this graph. This slide shows an example of what one of these friendship graphs might look like visually and the type of plot we aim to create, showing components versus network size. Here here along the x-axis the number of users n are plotted, and in the y-axis there are the connected components. Expected results. We expected a few key outcomes: a degree distribution showing how many friend users have the handshaking theorem, which states that the sum of all vertex degrees equal to twice the number of edges must hold true in our simulation. We hypothesize that as the network size n increases, the number of connected components would decrease. This is because with more users, there's a high chance of isolated groups becoming connected through new random friendships. And in conclusion, this project showed how graph theory provides a powerful tool to understand the structure of social network. Our simulation confirmed that larger networks tends to be more interconnected with fewer isolated components. It also successfully demonstrated theoretical properties like the handshaking theorem in a practical setting. So thank you for listening.